Welcome to Journey Through Time, the channel where curiosity drifts across epochs and history becomes a whisper before sleep. Tonight, we travel not just hundreds or thousands, but billions of years back, to an Earth unrecognizable, its skies alien, its air lethal to us. Yet, in that toxic world, life slowly prepared the conditions for birds to fly, whales to sing, and for you to listen now as your eyes grow heavy. Our story begins with the Great Oxidation Event, the quiet ancient revolution when life changed the atmosphere and nearly destroyed itself. Before oxygen filled the sky, Earth's rocks and oceans bore silent clues, banded iron formations stretching across ancient shields, sulfur isotopes telling cryptic stories, and the missing signatures of rust and oxygen in the earliest sediments. These traces whisper of a time when microbes without nuclei, hardy, alien to us, clung to hydrothermal vents, chemical soups, and shallow seas. Among them were cyanobacteria, tiny blue-green architects of change. They had mastered sunlight, using water and carbon dioxide to forge energy, releasing a waste product strange and deadly to their world, oxygen. To us, it means life. To them, it was poison, reactive and disruptive, like pouring acid into a fragile pool. At first, the oceans buffered it. Dissolved iron absorbed the new gas, rusting into red layers we find today. But once the iron was used up, oxygen escaped into the air. Slowly, imperceptibly, the atmosphere tilted toward something new, and almost every living thing faced extinction or retreat. This was Earth's first great biological crisis. No firestorm or asteroid, but suffocation by abundance. Microbes evolved defenses, retreated into anoxic refuges, or vanished. Meanwhile, oxygen's rise triggered the planet's first deep freeze, the Huronian glaciation, a possible snowball Earth. Even so, life endured, adapting and reorganizing. The quiet breath of cyanobacteria became the blueprint for future complexity, setting the stage for the emergence of cells with internal structures, and eventually, multicellular life. To understand how radical the Great Oxidation Event was, we must first picture Earth before oxygen. 3 billion years ago, the continents were little more than scattered fragments across a vast greenish ocean. The sun was weaker, its light filtered through thick hazes of methane and volcanic gases. No trees, no animals, no ozone to paint the sky blue, only rock, wind, and microbial mats clinging to tidal flats. The air reeked of sulfur and iron. Breathing it would have burned your lungs. In this alien environment, life was microbial and resourceful. Some lived off hydrogen and sulfur, others fermented in the dark, and a few clung to hydrothermal vents, thriving on chemical energy from the planet's interior. This metabolic diversity was the first sign of life's planetary power. Even before oxygen, microbes were already shaping climate by releasing methane, a greenhouse gas that kept the world warm under a dim sun. Cyanobacteria, however, unlocked something new, using water as an electron donor to photosynthesize. This process produced oxygen as waste, and once the ocean's iron was saturated, the gas escaped into the atmosphere. Sulfur isotopes record the shift. Mass-independent fractionation disappeared, replaced by patterns possible only in an oxygen-rich sky. Red beds, oxidized sediments, began forming on land. The chemical balance of the entire planet tipped. This was no overnight revolution, but a slow planetary seesaw. For millions of years, oxygen rose, fell, and rose again in pulses, like the breath of a sleeper. As methane levels dropped, Earth cooled. Glaciers crept toward the equator. The first known global ice age blanketed the planet, perhaps lasting tens of millions of years. Life retreated into refuges under ice, in brine channels, or near volcanic vents. But it survived. The microbe's waste gas had plunged the world into crisis, yet laid the groundwork for everything to come. The Great Oxidation Event was not merely chemical, it was evolutionary. Oxygen's appearance forced life to adapt or die. Anaerobic microbes evolved antioxidant enzymes to neutralize reactive oxygen species. Others embraced the enemy, developing aerobic respiration, a far more efficient way to harvest energy from food. This innovation enabled cells to grow larger, repair damage faster, and outcompete their anaerobic relatives. In this crucible of extinction and innovation, the first eukaryote-like cells emerged, larger, with internal compartments. They eventually formed symbioses with energy-producing bacteria, ancestors of our mitochondria. These mergers allowed cells to store energy at scale and build complex internal structures. Oxygen didn't just kill, it fueled the leap toward multicellularity, specialization, and complexity. Meanwhile, the planet itself was rusting. Iron-rich minerals on land oxidized, soils changed color, and new minerals appeared. The oceans stratified, surface waters carried oxygen, while the deep remained anoxic, creating steep chemical gradients. Microbes specialized for these layers, forming tightly linked communities where the waste of one fed another. Trace metals like molybdenum, zinc, and copper cycled differently under oxygen, reshaping the nutritional landscape of the seas. The ozone layer, a byproduct of free oxygen, began filtering ultraviolet radiation, making shallow waters safer and hinting at future colonization of land. The Earth's color palette shifted from dark reduced minerals to bright oxidized hues. These transformations created new ecological frontiers and chemical feedback loops, nutrient delivery from weathering, carbon burial in sediments, and the first hints of stable climate regulation. Through all of this, cyanobacteria kept working tirelessly in microbial mats, oblivious to the planetary upheaval their photosynthesis was causing. Their exhalations were transforming the atmosphere, ocean, and crust, turning Earth into a planet where life could one day stretch beyond the sea. After the initial rise of oxygen, Earth entered a long period sometimes called the Boring Billion, roughly 1.8 to 0.8 billion years ago. Oxygen levels stabilized at low but persistent concentrations. To the casual observer, little seemed to change. Yet beneath the surface, life was experimenting. Eukaryotes diversified, sexual reproduction evolved, and algae began branching into new forms. It was a slow accumulation of potential, a world holding its breath. During this time, tectonics and nutrient delivery set the stage for another oxygen surge. Continents grew, rivers fed phosphorus into shallow seas, and photosynthetic organisms bloomed. Each bloom produced more oxygen. Each burial of organic carbon locked away greenhouse gases, tilting the balance further toward an oxygenated planet. Around 800 million years ago, oxygen rose again, the Neoproterozoic oxygenation event, triggering new global glaciations, but also paving the way for complex multicellular life. The first large soft-bodied organisms, the Ediacaran biota, appeared. They were neither plant nor animal as we know them, but a strange early experiment in multicellularity. Then came the Cambrian explosion about 541 million years ago. Eyes, skeletons, predators, prey, and intricate food webs, all made possible by the energy unlocked through oxygen. Meanwhile, Earth's cycles matured. Carbon burial and weathering formed a delicate dance with atmospheric gases. Sulfur cycling rewrote ocean chemistry. The ozone shield strengthened, making land increasingly hospitable. Trace metals essential for enzymes became available in new ways, spurring innovation, Life's arms race accelerated. Antioxidants, repair systems, and symbioses evolved to manage oxygen's double-edged power. The Great Oxidation Event had cleared the rubble and rewired the planet. It did not directly create complex life, but created the conditions for it. Our mitochondria still bear its signature. Every breath we take is a legacy of cyanobacteria's quiet exhalations 2.5 billion years ago. And yet, even today, the balance of oxygen remains precarious, tied to carbon burial, forests, and the chemistry of our own actions. The Great Oxidation Event teaches us that planetary change is rarely a straight line. Oxygen's rise came in pulses and whiffs, a flickering lighthouse beam across a dark ocean. Scientists studying sulfur isotopes, carbon ratios, and banded iron formations see not a single event, but a complex sequence. Oxygen appearing locally, disappearing, then returning, until at last it became permanent. This uneven path left fingerprints. In some regions, mass-independent fractionation of sulfur isotopes reappears after vanishing, hinting at oxygen oases in shallow seas where cyanobacteria thrived, even as the global atmosphere remained mostly anoxic. Iron minerals in these layers show transitions between reduced and oxidized states, recording the tide of chemistry advancing and retreating over millions of years. Oxygen also interacted with other gases in destabilizing ways. Methane, the main greenhouse gas of early Earth, reacted with oxygen, collapsing into CO2 and water vapor. With methane weakened, global temperatures plummeted. The Huronian glaciation, Earth's first major ice age, wrapped the world in ice for tens of millions of years. Yet life clung on in hydrothermal refuges, brine channels beneath ice sheets, and sunlit cracks where light still reached. During these frozen epochs, volcanic CO2 kept accumulating in the atmosphere. With time, greenhouse warming overcame the ice, thawing the oceans. When sunlight returned to open water, nutrients stirred from the depths, fueling blooms of photosynthetic organisms and triggering yet more oxygen release. Each thaw and freeze cycle sharpened life's resilience and rewrote the carbon cycle. The very look of Earth was changing. Iron-rich rocks rusted to red, soils oxidized. New minerals appeared, some colorful, others rare, their chemistry impossible before free oxygen. Trace elements critical for enzymes, molybdenum, zinc, copper, shifted in availability, altering the evolutionary playing field. The ozone layer thickened overhead, filtering ultraviolet light and slowly preparing land for future colonization. Through all these upheavals, tiny cyanobacteria and their microbial successors continued exhaling. Their slow, relentless chemistry was carving the stage for multicellularity, metabolism, and eventually minds capable of telling this story. The aftermath of the Great Oxidation Event was not a triumphant sunrise, but a long adolescence for the planet. Oxygen levels spiked, fell, and rose again as Earth's systems searched for equilibrium. This wobble shaped the rules of recycling and resource flow still in force today. Sulfur cycling shifted dramatically. In an anoxic world, microbes handled sulfur mainly through sulfate reduction. With oxygen present, sulfates oxidized, and new pathways emerged, etched into the isotope record as global synchronized signals. Carbon cycling transformed too. Oxygen allowed rapid decomposition of organic matter, but burial of carbon locked oxygen in the atmosphere. This created a feedback loop. The more carbon buried, the more oxygen persisted, the more efficient decomposition became. The oceans stratified further. Surface waters oxygenated. Deep waters stayed anoxic for millions of years. This created chemical frontiers, forcing life to specialize and adapt. Anaerobes retreated into the deep, while oxygen-tolerant microbes flourished near the surface. Some of these lineages persisted for billions of years, ghosts of the Archean world still living in mudflats, our guts, and hydrothermal vents. Meanwhile, the ozone shield above continued thickening, absorbing ultraviolet light and making shallow waters safer. New minerals formed under oxidizing conditions. Weathering of continental crust changed river chemistry, feeding nutrients into the seas. Earth's color palette shifted permanently. Red beds appeared on land, signaling oxygen's reach beyond the ocean. In this dynamic environment, eukaryotes diversified. Larger cells with mitochondria could store more energy, evolve internal scaffolding, and experiment with multicellularity. Sexual reproduction arose, enabling genetic recombination and innovation. Algae spread, oxygenating surface waters even more and reinforcing the cycle. Slowly, patiently, Earth moved toward its next leap. Complex multicellular organisms with nervous systems, skeletons, and behavior. By about 800 million years ago, tectonic shifts and nutrient flows ignited another surge of oxygen, the Neoproterozoic Oxygenation Event. This second great breath of the planet coincided with new snowball Earth glaciations, but also with unprecedented biological innovation. The first large, soft-bodied organisms appeared, precursors to animals. Complex ecosystems began forming in shallow seas. This was possible because oxygen enabled more efficient metabolism. With aerobic respiration, cells could build tissues, circulate fluids, and develop nerves. Muscles, skeletons, and movement all rely on oxygen's energy. Without it, speed, coordination, and sentience cannot emerge. Thus, the groundwork laid by cyanobacteria, billions of years earlier, was finally bearing visible fruit. Earth's cycles matured further. The carbon cycle stabilized climate. Sulfur cycling maintained ocean chemistry. Ozone protected the surface. Trace metals became part of enzymes essential for photosynthesis and respiration. Each feedback loop reinforced the possibility of complexity. Then came the Cambrian explosion, about 541 million years ago. In a geological blink, animals with eyes, jaws, and skeletons diversified. Predators hunted prey, burrowers churned sediments, and intricate food webs formed. All of it rested on the foundation of oxygen, its energy, its risks, its selective pressures. Yet oxygen's legacy is double-edged. The same reactive molecule that powers life can destroy it. Throughout deep time, hydrogen sulfide upwellings, ozone-thinning episodes, and nutrient crises caused mass die-offs. These chemical accidents echo even today, warning us how delicate planetary balances can be. We are the descendants of survivors. Our mitochondria still breathe oxygen. Our cells still wield antioxidant defenses forged in ancient oceans. Every heartbeat and breath is a living fossil of a microbial revolution that almost ended life, but instead opened the door to everything we know. As Earth's oxygen levels rose, the chemistry of land, sea, and air became deeply intertwined. Volcanic gases reacted with the new atmosphere to form acidic aerosols that cooled the planet. Rivers carried oxidized minerals from weathered continents to the oceans, feeding new blooms of photosynthesizers and accelerating the burial of organic carbon. The entire crust became part of a self-reinforcing cycle. Trace metals essential to life shifted behavior under oxygenated conditions. Elements like molybdenum, copper, and zinc became more available for enzymes, enabling metabolic pathways previously impossible. Iron, once abundant in soluble form, now precipitated out as rust, depriving microbes of a key nutrient. Phosphorus became trapped in oxidized sediments, limiting primary production until tectonic uplift released it again. Each constraint or release spurred new adaptations, new experiments in living chemistry. Meanwhile, hydrogen sulfide in deep anoxic waters emerged as a powerful antagonist. When upwelling currents brought H2S to the surface, it poisoned aerobic organisms and destroyed ozone, thinning Earth's protective shield. Some scientists argue these ocean burps triggered mass extinctions and delayed the spread of complex life. Even after oxygen appeared, the planet remained a chemical battleground, and survival meant constant innovation. The eukaryotic cell, our ancestor, was one such innovation. Born from symbiosis between an archaeon and a bacterium, it used oxygen to generate unprecedented amounts of energy. Mitochondria powered bigger cells, internal transport systems, and the first steps toward multicellularity. This leap in energy capacity set the stage for communication between cells, tissue specialization, and eventually nervous systems. Oxygen's danger became its greatest gift. The Great Oxidation Event also reshaped Earth's climate system. Methane depletion cooled the planet, leading to snowball episodes that lasted millions of years. But once ice retreated, sunlight penetrated the seas, mixing nutrients and sparking blooms of photosynthetic organisms. This created pulses of oxygenation, burial of carbon, and feedback loops that stabilized climate over time. Carbon cycling became faster and more efficient. Oxygen allowed organic matter to decompose quickly, recycling nutrients but also tying atmospheric O2 to the burial of carbon. If burial slowed, oxygen fell. If burial accelerated, oxygen rose. This delicate dance still governs our atmosphere today. Above, ozone formed a thin but vital veil. By filtering ultraviolet radiation, it protected DNA from lethal damage and allowed microbes to inhabit shallower waters. Over eons, the shield strengthened, making land surfaces less hostile. Clay minerals on continents began to hold water and nutrients, creating potential niches for future terrestrial colonization. Eukaryotes diversified quietly through the boring billion. Sexual reproduction appeared, reshuffling genes and increasing adaptability. Algae expanded, oxygenating surface waters and reinforcing atmospheric O2. Symbioses flourished. One organism's waste became another's resource, forming complex microbial consortia that mirrored future ecosystems. By 800 million years ago, tectonic and climatic shifts ignited a second great oxygen surge. Nutrients flooded into oceans, multicellular organisms appeared, and glaciers advanced again. This repeating cycle of ice, oxygen, and innovation acted as an evolutionary engine, sharpening resilience and unlocking new biological strategies. Then came the Cambrian explosion, a punctuation mark in the history of life. Around 541 million years ago, oxygen levels reached a threshold that supported rapid diversification. Within a geologic blink, animals with eyes, shells, skeletons, and complex behaviors populated the oceans. Food webs became intricate, predation intensified, and ecosystems grew dynamic. Oxygen enabled muscles, nerves, and circulation, the foundation for movement and sensory perception. Without oxygen's energy yield, complex multicellularity and behavior could not have evolved. The very possibility of brains, reflexes, and sight arose from cyanobacteria's ancient photosynthesis. Earth's surface reflected these changes. Weathering accelerated under an oxygenated sky, delivering nutrients to coastal waters. The ozone layer shielded the surface from UV, allowing larger organisms to venture into shallower zones. Trace metals cycled in new ways, some becoming cofactors for enzymes essential to collagen, hemoglobin, and other building blocks of animal life. Yet oxygen's legacy remained double-edged. Hydrogen sulfide events, nutrient lockouts, and climatic swings caused periodic die-offs. Each extinction restructured ecosystems and pushed survivors to adapt. This pattern, crisis followed by innovation, became a defining rhythm of Earth's biosphere. We are living proof of that rhythm. Every mitochondrion in our cells is a relic of the Great Oxidation Event, using oxygen to extract energy with breathtaking efficiency. Every breath is an echo of a microbial mistake that nearly wiped life out, but ultimately made complex organisms possible. The balance remains fragile. Atmospheric oxygen depends on photosynthesis, carbon burial, and the chemistry of our own planet-shaping activities. By the time Earth entered the Paleozoic era, oxygen had become a permanent atmospheric feature, but its levels were anything but static. Geological records show pulses of increase and periods of decline, each reshaping climate and life. These swings illustrate the core lesson of the Great Oxidation Event. Planetary chemistry is a dynamic system of feedback loops, not a one-way road. Sediments and isotope ratios reveal that after the Cambrian explosion, ocean oxygenation remained incomplete. Deep basins stayed anoxic for millions of years, creating ecological frontiers where anaerobes survived as relics of a bygone world. In shallower waters, aerobic organisms expanded, building reefs, skeletons, and complex food webs. This stratified ocean drove evolutionary divergence, forcing organisms to specialize for oxygen-rich or oxygen-poor niches. Weathering of newly formed mountain ranges released nutrients like phosphorus, fueling blooms of photosynthetic plankton. Each bloom produced oxygen, but also created dead zones when it died and decomposed. These alternating phases of productivity and anoxia kept Earth's biogeochemical cycles unstable, but also generated evolutionary pressure. Organisms adapted by forming symbioses, developing more efficient metabolisms, and experimenting with body plans and behaviors. Above, the ozone layer thickened, cutting UV flux to the surface and making shallow marine environments more habitable. Trace metals cycled in increasingly complex ways. Molybdenum, copper, and iron became limiting factors, pushing organisms to evolve transport proteins, storage systems, and biochemical substitutes. Even the rise of collagen and other structural molecules in animals reflects the availability of certain metals tied to oxygenated conditions. As scientists reconstruct this deep past, they rely on multiple lines of evidence: geochemistry, paleontology, and experimental simulations. Sulfur isotopes mark the disappearance of mass-independent fractionation, pinpointing when oxygen crossed a critical threshold. Carbon isotopes show enhanced burial of organic matter, revealing when oxygen began to persist in the atmosphere. Iron formations chart the ocean's rusting, recording the gradual depletion of dissolved iron as oxygen took hold. Together, these proxies form a planetary diary, written in atoms. The story they tell is not simply one of biological innovation, but of coevolution between life and planet. Cyanobacteria created oxygen, but tectonics controlled nutrient delivery. Volcanic gases set the background chemistry, and continental growth altered the sinks that absorbed or released gases. This interplay turned Earth into a self-modifying system. Every pulse of oxygen altered rock weathering, which in turn changed nutrient flows, which fed back into photosynthesis. Even today, Earth's oxygen budget is precariously balanced. Photosynthesis produces oxygen, but respiration and decay consume it. Burial of organic carbon tips the scale. If burial slows, oxygen drops. If burial accelerates, oxygen rises. This mechanism, born during the Great Oxidation Event, still governs our atmosphere. Understanding this balance has transformed not only Earth science, but also astrobiology. Oxygen in an exoplanet's atmosphere is no simple sign of life. It could be transient, localized, or the product of non-biological processes. Earth itself was inhabited for billions of years before oxygen became detectable. Thus, the GOE serves as a cautionary tale. A planet can teem with life, yet show no obvious biosignature, or flash an oxygen signal without sustaining it. The human discovery of the Great Oxidation Event is itself a story of patience and curiosity. For most of history, no one imagined Earth's air had changed. Only in the 20th century did geologists, following iron and sulfur clues, realize the planet had once been airless and that microbes had built the sky. Mining for iron in Canada, Western Australia, and South Africa exposed vast banded iron formations. Isotopic analysis revealed sulfur signatures vanishing at 2.45 billion years ago. Paleosols turned from reduced to oxidized. Piece by piece, a picture emerged of a planetary revolution. Key figures like Preston Cloud argued that oxygenation was the single most important transformation in Earth's history, biological innovation on a planetary scale. James Lovelock's Gaia hypothesis, though controversial, reinforced the idea that life and planet act together, regulating each other. By the 1980s, Earth system science became a formal field, integrating geology, biology, chemistry, and climate into a single framework. Today, scientists use lab experiments to simulate ancient oceans, pumping gases into tanks seeded with microbes to test hypotheses. Could iron really mop up early oxygen? Could sulfur cycling explain isotopic shifts? How fast would methane collapse in the face of rising O2? These experiments complement field studies, drilling ancient cratons and analyzing sediment cores, grain by grain. Together, they reveal a story not of abrupt revolution, but of slow, persistent transformation. This narrative reshapes our sense of time and power. Tiny cells, working over eons, transformed not just their environment, but the planet's fate. Our mitochondria, our breath, even our consciousness trace back to that microbial experiment. We inherit not just oxygen, but a lesson that small, sustained actions can alter a world. The Great Oxidation Event's legacy continues into the fabric of our own bodies. Every mitochondrion in our cells is a living fossil of the first aerobic partnership, still turning oxygen into energy with astonishing efficiency. Every antioxidant enzyme traces back to ancient defenses forged in seas, where oxygen was both power and poison. This molecular memory shows how crisis and opportunity were fused in early evolution. Earth's surface, meanwhile, kept responding to oxygen. Weathering hardened the crust, creating clays that could store water and nutrients. Rivers delivered these minerals to coasts, fertilizing photosynthetic blooms and accelerating carbon burial. This deep-time feedback loop linked erosion, nutrient supply, biological productivity, and atmospheric composition, a self-regulating system that still operates today. Minerals tell the same story. Many of Earth's most colorful oxides and familiar ores, hematite, goethite, manganese nodules, exist because oxygen appeared. Even trace metals used in our electronics and enzymes were cycled differently after the GOE. The palette of the Earth literally brightened, a chemical signature of life's influence. And still, pulses of instability could erase progress. Hydrogen sulfide events and nutrient lockouts may have repeatedly thinned the ozone layer, exposing surface life to UV spikes and causing local extinctions. Yet each setback reshaped ecosystems, selecting for more resilient organisms and driving further innovation. Crisis and adaptation became Earth's recurring rhythm. By the Neoproterozoic, around 800 million years ago, oxygen rose again, and glaciers swept across the globe. But this time, multicellular life had a foothold. Large, soft-bodied ediacaran organisms flourished in oxygenated shallow seas, forming some of the first complex ecosystems. They were soon replaced by more active animals, but their existence marked the threshold crossed. Life had moved beyond single cells into visible macroscopic forms. The Cambrian explosion, following shortly after, turned the ocean into a living tapestry. Animals with shells, eyes, and limbs diversified rapidly. Predation drove innovation. Spines, burrows, skeletons, nervous systems. All of these required oxygen's high-energy metabolism. Without it, speed, sensory processing, and large body size would have been impossible. Oxygen also allowed Earth's cycles to lock into a new stability. Carbon burial moderated climate, ozone shielded life from UV, and trace metals fueled enzymatic diversity. As continents drifted and mountain ranges rose, rivers carried nutrients into the seas, supporting plankton blooms that reinforced atmospheric oxygen. The biosphere had reached a self-sustaining feedback loop powerful enough to support complexity indefinitely, yet still vulnerable to shocks. Each mass extinction that followed, the Ordovician-Silurian, the Devonian, the Permian Great Dying, reset ecosystems, but also opened niches for survivors. This pattern echoed the GOE itself, crisis clearing the way for innovation. The rhythm of life and planet was now set. Feedback, extinction, rebirth, complexity. Today, when scientists study the Great Oxidation Event, they see not just a historical curiosity, but a mirror for our own time. Microbes once transformed their world inadvertently. Humans are now transforming ours knowingly, altering the carbon cycle, warming the climate, and reshaping oceans. The same feedbacks that once plunged Earth into ice ages or oxygen pulses still operate, only now we drive them faster. Astrobiologists use the GOE as a guide to search for life elsewhere. Oxygen is a powerful biosignature, but Earth shows it can be misleading. For billions of years, life existed without detectable oxygen, and even after it appeared, it flickered before stabilizing. Thus, finding O2 on another planet could mean a living biosphere, or merely a transient chemistry. Our own world is the calibration point. The lesson of the GOE is that small, steady processes can accumulate into global transformations. Cyanobacteria did not plan to oxygenate Earth, yet they did. We too are altering planetary chemistry, only far more quickly. Understanding deep time teaches humility and urgency. The loops of feedback, once invisible, now respond to us. And at the deepest level, the GOE is a story of possibility. From poison came power. From crisis came complexity. From invisible microbes came the foundation of consciousness, culture, and curiosity. Every breath you take is an echo of that revolution, a thread connecting your life to a world of rusted oceans and frozen continents 2.5 billion years ago. The rise of oxygen also reshaped the invisible architecture of the biosphere, the cycles of carbon, sulfur, nitrogen, and trace elements. Before oxygen, carbon burial was slow and incomplete. Methane was abundant. Sulfur circulated mainly as hydrogen sulfide, and nitrogen chemistry was limited. After oxygen, all of these loops were rewritten. Decomposition became faster. Carbon dioxide was released more efficiently. Sulfates replaced sulfides, and nitrification expanded. Life was no longer simply reacting to its environment. It was engineering it. This reorganization extended deep into Earth's crust. As oxidizing conditions spread, new mineral families appeared. Uranium and other metals shifted to more soluble states, altering groundwater chemistry. Clay-rich soils formed, holding moisture and nutrients, laying the groundwork for future terrestrial ecosystems. Rivers carried dissolved elements far from their source. linking continents to oceans in a single global system. In the oceans, chemical stratification created a double world, an oxygenated upper layer supporting increasingly complex organisms, and an anoxic deep ocean harboring ancient metabolic pathways. At the boundaries between these zones, microbes learned to exchange electrons between metals, sulfur, and gases, pioneering redox reactions that still underpin our planet's biogeochemistry. Oxygen's rise also forged the first global climate stabilizer. With methane diminished, Earth's thermostat shifted to carbon dioxide and rock weathering. CO2 from volcanoes built up slowly, but was drawn down by silicate weathering and carbon burial, buffering climate over millions of years. This carbonate-silicate cycle, strengthened under oxygenated conditions, helped keep Earth habitable, even as the sun brightened. By the time multicellular organisms became established, Earth's atmosphere and oceans were no longer just backgrounds for life. They were products of it. Photosynthesis, respiration, burial, and weathering had locked into a feedback system that regulated climate and oxygen for hundreds of millions of years. Yet this system was dynamic, not static. Fluctuations in oxygen correspond to pulses of innovation and extinction in the fossil record. When oxygen rose, body size and complexity increased. When it fell, ecosystems contracted. These oscillations show that even stable oxygen levels mask a constant negotiation between sources and sinks, between photosynthetic production and oxidative loss, between burial and release of organic matter, between volcanic outgassing and rock weathering. Trace metals became a silent engine of evolution. The availability of molybdenum, vanadium, and copper influenced which enzymes could evolve and which metabolic pathways could flourish. These micronutrients were tied to redox conditions, meaning Earth's chemistry set limits on biology's imagination. In turn, biology altered the chemistry, a feedback loop echoing the earliest days of life. Above, the ozone layer matured into a robust filter. With ultraviolet radiation subdued, DNA mutation rates dropped, making long-term heredity more stable. This protection allowed organisms to explore shallower waters, and eventually, land surfaces without lethal UV bombardment. Each small step on this path built toward the eventual colonization of continents by plants and animals hundreds of millions of years later. In modern science, the Great Oxidation Event stands as the archetype of planetary scale change driven by life. It demonstrates that evolution is not confined to organisms, but can restructure oceans, crust, and sky. It also reveals that such transformations are rarely benign for existing life, but can open doors for entirely new forms to arise. Researchers now use the GOE as a lens for understanding mass extinctions and climate transitions. The same principles, feedback loops, chemical thresholds, tipping points, govern events from snowball Earth episodes to greenhouse spikes and ocean anoxia in the Phanerozoic. This deep time perspective shows how small shifts accumulate, crossing invisible lines into planetary upheaval. Astrobiologists extend this lesson to exoplanets. Oxygen, methane, and other gases become clues to alien metabolisms, but also to instability. A world rich in oxygen might harbor life, or might be experiencing its own microbial revolution, complete with extinctions and climate shifts. The GOE warns us to interpret such signals carefully. For humanity, the GOE is both inspiration and caution. Microbes, through slow chemistry, transformed their world unintentionally. We are transforming ours intentionally, but much faster, altering the carbon cycle, warming the climate, acidifying oceans, and reducing biodiversity. The same feedbacks that once plunged Earth into ice ages or oxygen surges still operate, only now on human timescales. Recognizing these patterns may help us avoid the harshest outcomes and guide our own planetary stewardship. When we trace the Great Oxidation Event across deep time, one theme repeats: resilience through transformation. Life's earliest chapters show that stability is not the natural state of a biosphere. Feedbacks, chemical loops, and environmental thresholds constantly push it toward new equilibria. Cyanobacteria altered the sky, not because of intent, but because of metabolism. The Earth's rocks and oceans responded with rust, ice, and a rearranged climate system. This interaction rewired every major cycle. The carbon cycle shifted from methane-dominated greenhouse warmth to carbon dioxide-driven buffering. The sulfur cycle shifted from hydrogen sulfide to sulfate-based pathways, etching its record in isotopic variations worldwide. The nitrogen cycle diversified under oxygen, supporting enzymes that transformed ammonium into nitrate, opening new food chains and niches. Each of these loops began with a microbial process, yet each reverberated through continents and atmospheres. In the oceans, stratification became a template for diversity. An oxygen-rich surface supported photosynthetic plankton. An anoxic deep ocean housed ancient metabolisms. At their interface, chemical gradients fueled microbial consortia that exchanged electrons between metals, gases, and organic molecules. This invisible frontier trained evolution in cooperation and specialization, a rehearsal for multicellular complexity. Above, the ozone layer thickened further, shielding surface waters and coastal zones. With ultraviolet light filtered, DNA damage decreased, allowing lineages to persist longer and accumulate mutations gradually. This set the stage for evolutionary leaps like multicellularity and nervous systems, which require stable heredity over long timescales. The world was no longer simply a backdrop, but a co-creator of life's possibilities. The Great Oxidation Event also reframed our understanding of time. Before isotopic analysis, geologists thought of Earth's history as a series of static eras punctuated by occasional catastrophes. The GOE showed that invisible processes, chemical reactions, microbial metabolisms, slow burial, could drive planetary shifts as profound as asteroid impacts. This insight birthed Earth system science, which views air, water, rock, and life as a single dynamic engine. We now know that planetary change does not always require sudden violence. It can arise from steady, small actions compounded over eons. Cyanobacteria exhaled oxygen molecule by molecule, but over hundreds of millions of years, they transformed the atmosphere, oceans, and crust. This is why climate scientists look to the GOE for analogies. It shows how persistent fluxes cross tipping points into new states. Astrobiology draws another lesson. Biosignatures are time-dependent. An exoplanet could be alive but invisible to our instruments if its life has not yet changed the atmosphere. Or we might see oxygen and assume flourishing biology where only transient chemistry exists. Earth itself has played both roles across its 4.5 billion year history. Even our own existence reflects the GOE's legacy. Mitochondria use oxygen to produce ATP, making possible large brains, endurance, and complex behaviors. Our immune systems deploy reactive oxygen species as weapons against pathogens, a molecular echo of the ancient struggle between life and oxygen. The entire human condition, from running marathons to composing music, rests on an energy system invented by microbes billions of years ago. Seen from this perspective, the Great Oxidation Event is not just an episode in geology, but a universal principle, that life and environment co-evolve through feedback and crisis. Microbes changed the air changed the oceans changed the rocks changed the climate changed life again. This looping causality forged the template for every future transformation, from the Cambrian explosion to modern climate change. Scientists working on the GOE embody this looping curiosity. They drill cores from billion-year-old cratons, grind rocks into powder, and run mass spectrometers to read isotope ratios like lines of poetry. They simulate ancient oceans in sealed glass tanks, adding gases and microbes to watch chemistry evolve. Each experiment tests a small piece of a vast puzzle whose full picture spans continents and eons. Their findings extend beyond Earth. If life could rewire a whole planet here, it could do so elsewhere. Oxygen or other reactive gases might appear on exoplanets, not because of geology, but because of biology. But the GOE also warns that such transformations can be catastrophic for existing life before they open new possibilities. This double-edged pattern, poison becoming power, is likely universal wherever life evolves. For humanity, this is a mirror. We too are a planetary force, altering carbon cycles, ocean chemistry, and atmospheric composition. The GOE shows how feedbacks operate, how tipping points can trigger ice ages or mass extinctions, and how recovery takes millions of years. Our challenge is to understand these loops well enough to steer through them deliberately, rather than blindly. The Great Oxidation Event also reshaped the very surface of Earth. Before oxygen, continents were bare stone washed by acidic rains. After oxygen, weathering produced soils capable of retaining water and nutrients. Clay minerals, iron oxides, and newly stable compounds blanketed the land, creating a chemical bridge between continents and oceans. Rivers became nutrient highways, carrying phosphorus, trace metals, and organic matter to coastal zones, fueling photosynthesis and reinforcing atmospheric oxygen. This new interplay between land and sea set off feedback loops that stabilized climate. Silicate weathering drew down CO2. Burial of organic carbon sequestered greenhouse gases. Oxygen allowed for more efficient decomposition, recycling nutrients, but also tying the fate of atmospheric composition to burial rates. The Earth had, in effect, built its first planetary thermostat, a system robust enough to buffer a brightening sun, but delicate enough to collapse under extreme perturbation. Meanwhile, the oceans themselves grew more complex. Oxygenated surface waters supported plankton blooms. Mid-depths oscillated between oxic and anoxic states. The deep remained largely reducing for millions of years. At these chemical boundaries, microbes evolved intricate metabolisms, exchanging electrons across minerals, gases, and organic substrates. This invisible frontier nurtured the first consortia resembling ecosystems, communities whose interdependence foreshadowed multicellularity. Above, the ozone layer thickened still further, drastically cutting ultraviolet flux and allowing DNA-based life to persist in shallower zones. This protection, combined with nutrient-rich waters, provided the stable conditions necessary for larger, more complex organisms to emerge. In essence, oxygen transformed not only the chemistry of the planet, but the very architecture of habitability. From the perspective of modern science, the Great Oxidation Event is the prototype for how life and environment co-author planetary change. Each line of evidence, sulfur isotopes, carbon ratios, iron formations, red beds, tells part of the same story. A slow accumulation of oxygen, interrupted by pulses and crashes, until a new equilibrium emerged. The event's timing, around 2.4 to 2.3 billion years ago, marks a planetary tipping point, as consequential as any asteroid impact or supervolcano. This recognition has reframed our search for life beyond Earth. Astrobiologists now treat oxygen not as a definitive biosignature, but as a dynamic variable. A planet may be teeming with microbes long before oxygen accumulates. Conversely, oxygen may appear transiently due to abiotic processes. Earth itself would have fooled distant observers for billions of years, first as lifeless though inhabited, then as oxygen-rich, but unstable. The GOE thus serves as both model and warning for interpreting exoplanet atmospheres. It also offers a template for understanding human-driven change. We are altering atmospheric composition on a timescale thousands of times faster than cyanobacteria did. We can watch feedbacks unfold in real time: ice melting, oceans acidifying, forests burning, mirroring deep time patterns of destabilization. The GOE shows that once a threshold is crossed, recovery can take millions of years. Recognizing that timescale may help guide policy and stewardship today. In a deeper sense, the GOE reminds us that life is not passive. Even without intention, it remakes worlds. We stand on the shoulders of microbial alchemists who taught our planet to breathe, and their legacy is our inheritance. Every lungful of air, every spark of metabolism, every neural impulse owes its existence to their ancient chemistry. Finally, the Great Oxidation Event forces us to rethink evolution itself. Rather than a linear ascent from simple to complex, it appears as a series of bottlenecks, crashes, and rebounds. Oxygen's rise was catastrophic for existing life, but essential for future life. The pattern recurs across history: extinction clearing niches, survivors innovating, ecosystems reorganizing. Complexity often blooms from collapse. This lesson echoes in the fossil record after the GOE. Mass extinctions, whether triggered by volcanism, asteroid impacts, or climatic upheaval, repeatedly prune the tree of life. Yet each time, survivors diversify into new forms, often more complex than before. This dynamic owes much to the energy unlocked by oxygen, its capacity to power large bodies, fast metabolisms, and intricate behaviors. The GOE also reframes humanity's place in nature. We are not an exception, but another expression of planetary feedback. Our industrial metabolism mirrors microbial metabolism in its planetary reach. The difference is speed and awareness. Where cyanobacteria acted over hundreds of millions of years, we act in centuries. Where they exhaled oxygen unknowingly, we emit carbon knowingly. Understanding this parallel underscores our responsibility. Looking forward, the GOE suggests that stability is not guaranteed. Oxygen levels today are balanced between photosynthesis and respiration, between forests and oceans, between burial and decay. Disturbances to these processes can tip the balance, just as they did in the deep past. Recognizing our interconnection with these loops is the first step to managing them wisely. Across the immensity of geologic time, the Great Oxidation Event stands as one of the few true revolutions. Before it, Earth was a microbial world of chemical gradients and alien skies. After it, the planet bore the seeds of forests, animals, and eventually human minds. Yet this revolution did not come as a sudden flash, but as a drawn-out negotiation between metabolism and mineral, atmosphere, and ocean. The oxygen catastrophe, as some geologists call it, exterminated vast lineages of anaerobes, but also created new energy landscapes. Aerobic respiration yielded orders of magnitude more ATP than fermentation, making large, complex cells feasible. Mitochondria, born from endosymbiosis, transformed this energy into architecture: internal skeletons, transport networks, signaling pathways. Without oxygen, cells could not afford such luxuries. This new biochemistry reshaped ecosystems. Microbes formed layered mats, with oxygen producers on top and anaerobes below, exchanging metabolites in intricate cycles. Trace metals catalyzed reactions impossible before. DNA repair systems evolved to handle oxidative stress. Cell membranes incorporated sterols, stabilizing larger, more active cells. Each microscopic innovation left a planetary-scale imprint. Geology, too, bore witness. Banded iron formations ceased as oceans rusted out. Red beds spread across continents. Uranium deposits shifted from insoluble to soluble forms. Sulfate evaporates appeared, marking altered seawater chemistry. The crust itself became a different chemical entity under oxygen's influence. Our modern continents, soils, and ores owe their composition to this ancient breath. As oxygen accumulated, it enabled new ecological strategies. Predation, for instance, requires fast movement, sensory coordination, and efficient energy use, all oxygen-dependent. Likewise, burrowing into sediments, building reefs, and pumping fluids through body cavities demand high metabolic rates. Thus, the rise of oxygen was also the rise of animal behavior. This feedback loop continued through mass extinctions and recoveries. After each crisis, oxygen-rich survivors diversified into novel forms. Nervous systems, muscles, and circulatory systems refined energy use further. Skeletons mineralized, ecosystems became three-dimensional, and biogeochemical cycling accelerated. In essence, oxygen transformed Earth from a flat microbial carpet into a layered, dynamic biosphere. Astrobiology now treats this as a template for planetary evolution. A world may begin as microbial and anaerobic, then experience a biogenic atmospheric shift, followed by a burst of complexity. Each stage may last hundreds of millions of years, or stall entirely. The GOE is our only data point for such a transformation, making it a cornerstone of comparative planetology. We also glimpse our own reflection. Human civilization, like cyanobacteria, transforms atmospheric composition, but in decades, not eons. We are accelerating feedback loops that once unfolded over deep time. Recognizing this scale difference is crucial. If recovery from a tipping point once took millions of years, the biosphere cannot easily rebound on a human timescale. Ultimately, the Great Oxidation Event is a story of paradox. A waste product became the basis of life. A poison became a power source. Catastrophe became opportunity. This pattern, innovation emerging from crisis, pervades evolution and human history alike. In the GOE, we see the blueprint of resilience, networks, feedbacks, and cooperation outlasting shocks. Microbes survived snowball Earths, hydrogen sulfide poisonings, and nutrient lockouts. They adapted antioxidant systems, formed symbioses, and built the first global ecosystems. These same principles, redundancy, flexibility, interdependence, sustain complex systems today, from rainforests to economies. The GOE also challenges our sense of agency. No single organism planned to change the atmosphere, yet collectively, their metabolism remade the world. This emergent power parallels our own, billions of individual actions summing to planetary scale impact. Understanding this emergent dynamic is key to steering our future. And at the deepest level, the GOE links our breath to the earliest light of the sun, filtered through ancient seas. Each inhalation carries atoms forged in stars and cycled through cyanobacteria billions of years ago. We are not merely descendants of the Great Oxidation Event. We are its continuation, living proof of its transformative power. Seen through the lens of deep time, the Great Oxidation Event becomes more than geology. It becomes biography, the biography of a planet awakening to complexity. Before oxygen, Earth's surface chemistry was dominated by reducing gases and dissolved metals. After oxygen, the atmosphere gained a reactive shield, the oceans stratified, and the crust transformed into a palette of oxides and clays. This shift produced the raw materials of modern continents, ores, and soils. This planetary makeover also set the stage for the rise of ecosystem engineering at a global scale. Photosynthetic organisms began not only to fill niches, but to alter their environment in ways that fed back to support their expansion. An early echo of how forests later stabilized climate or coral reefs built habitats. In each case, biology created conditions for its own flourishing, while also risking collapse if feedbacks overshot. Trace metal availability served as a hidden throttle on this process. The solubility of iron, copper, and molybdenum shifted with redox conditions, making enzymes more or less viable. Organisms adapted by evolving new pathways or by living in microhabitats where the right metal mix persisted. This tight coupling between geochemistry and evolution meant that planetary changes literally shaped the limits of metabolism. Above, the ozone layer transformed sunlight from a lethal barrage into a filtered glow, allowing DNA-based life to spread. With less UV damage, hereditary information could accumulate steadily, enabling complex developmental programs. Over time, these programs produced multicellular bodies, coordinated behaviors, and eventually neural networks capable of processing information and forming memories. The seeds of consciousness. The Cambrian explosion that followed hundreds of millions of years later can be seen as the visible flowering of the invisible groundwork laid by the GOE. Without oxygen, muscles cannot contract rapidly, nerves cannot fire quickly, and collagen cannot form robust tissues. With oxygen, all of these became possible at once, unlocking predation, locomotion, and sensory organs. This diversification reshaped the ocean floor. Burrowing animals oxygenated sediments, changing nutrient cycles, and further stabilizing oxygen levels. Reefs built by early animals altered wave action and sediment deposition. The biosphere and geosphere became locked in a mutual dance, each shaping the other in real time. At the same time, extinction remained a companion. Every surge of complexity was followed by crashes, Ordovician glaciation, Devonian crises, Permian die-offs. Each event pruned ecosystems, but left survivors with new opportunities, echoing the pattern of the GOE itself. Crisis as the crucible of innovation. For scientists today, these deep time patterns reveal how energy flow governs complexity. Higher energy availability, whether through oxygen, sunlight, or chemical gradients, enables larger, more intricate systems. But it also increases vulnerability to disruption. The GOE stands as the first and greatest demonstration of this principle. In the modern era, our understanding of the Great Oxidation Event has become increasingly interdisciplinary. Geologists measure isotope ratios, microbiologists culture ancient-like microbes, climate modelers simulate early atmospheres, astrobiologists compare Earth's evolution to exoplanet possibilities. Together they form a new narrative in which life and planet are inseparable actors in a cosmic drama. This narrative carries implications far beyond academic curiosity. It informs how we interpret oxygen detections on distant worlds, how we model climate feedbacks today, and how we think about resilience in complex systems. It teaches that small agents can drive global change, that feedbacks can surprise, and that recovery can be unimaginably slow. It also reframes our sense of identity. We are not merely living on Earth, but living in Earth, a system whose air, water, and rock are co-produced by life itself. Every lungful of air, Every drink of water, every bite of food is the end of a chain, stretching back to cyanobacteria under an alien sky. And it deepens our sense of continuity. The oxygen you breathe was once bound in rock, released by microbes, cycled through countless generations of organisms, and only then arrived in your bloodstream. You are, at a molecular level, part of a 2.5 billion-year-old experiment in planetary transformation. Looking back, the Great Oxidation Event can be seen as the first true example of a self-organizing, self-modifying biosphere. Before it, Earth's environment largely followed physical and chemical rules set at planet formation. After it, biology began to dominate, dictating the chemistry of oceans, atmosphere, and crust. Life no longer merely adapted to conditions, it created them. This marks a fundamental shift in planetary evolution. Microbes on early Earth released oxygen as a byproduct, but that byproduct became a geochemical force, altering redox states and mineral forms, cooling the climate, and setting off a cascade of feedback loops. Once oxygen gained a foothold, it amplified itself. New metabolic pathways flourished, carbon burial increased, ozone shielded the surface, and more complex ecosystems reinforced the process. Every step along this path left physical evidence. Banded iron formations gave way to red beds. Sulfur isotopes lost their mass-independent fractionation. Uranium deposits shifted from insoluble to soluble forms. The boring billion of low but persistent oxygen marked a slow maturation, preparing the way for multicellular life. Without these slow transitions, the Cambrian explosion could not have occurred. This interplay also shows that planetary transformation can happen without a conscious agent. Billions of cells acting locally produced a global revolution. Their collective metabolism reshaped climate, oceans, and rocks, ultimately making it possible for conscious observers to emerge and tell the story. This lesson, that local actions can have planetary consequences, resonates deeply in our own era. As oxygen rose, Earth's surface became more dynamic and interconnected. Rivers carved continents and fed deltas. Deltas nourished plankton blooms. Plankton blooms buried carbon and sustained oxygen. Mountain building exposed fresh rock to weathering. Weathering drew down CO2, cooling climate and feeding more nutrients to the sea. The biosphere and geosphere formed a single machine with countless feedback loops. This machine's efficiency increased with oxygen. Aerobic microbes decomposed organic matter faster, recycling nutrients and sustaining higher productivity. Eukaryotes with mitochondria could exploit richer energy sources, building larger bodies and more complex communities. Predation, mobility, and sensing all became feasible, transforming flat microbial mats into intricate three-dimensional food webs. Meanwhile, the ozone layer continued to strengthen, thick enough by the mid-Proterozoic to significantly reduce DNA-damaging UV radiation. This protection allowed life to creep closer to the surface and eventually onto land. Clay-rich soils formed, storing water and nutrients, ready for the first terrestrial photosynthesizers hundreds of millions of years later. Oxygen was not merely a gas, but a planetary technology, enabling new experiments in living. The GOE also seeded Earth with minerals critical to future civilization. Many of our iron ores, copper belts, and uranium deposits formed under or because of oxygenated conditions. In a sense, modern industry still draws directly on the consequences of that ancient microbial revolution. Every steel beam, every circuit board, every nuclear reactor owes its raw materials to the first oxygenation of Earth. Today, when we model exoplanets, the GOE provides our single best analog for atmospheric transformation by life. We know from Earth's record that oxygen can appear slowly, flicker, stabilize, and then drive bursts of complexity. We know that minerals, isotopes, and surface colors can shift dramatically under changing redox conditions. And we know that even after oxygen appears, a planet can remain hostile or unstable for hundreds of millions of years. This understanding shapes telescope missions searching for biosignatures. When we see oxygen or ozone in a distant atmosphere, we now ask, is it steady or transient? Is it accompanied by methane, which would signal disequilibrium and thus biology? Does the planet's surface show iron rusting or other redox clues? Without the GOE, we would lack this nuanced framework. For Earth itself, the GOE remains a living influence. Atmospheric oxygen is still balanced by photosynthesis, respiration, and burial of organic carbon. Human activities that clear forests, erode soils, and alter oceans disturb this balance. Though oxygen levels change slowly compared to carbon dioxide, the same principles apply: sources and sinks, feedback loops, tipping points. The GOE warns that once a system crosses a threshold, recovery can take far longer than human lifespans or civilizations. At the most personal level, the GOE connects our breath to cosmic history. Each inhalation contains atoms forged in stars, once dissolved in ancient oceans, cycled through microbes, and only then freed to the sky. We are breathing deep time, living evidence of a planetary experiment still underway. The Great Oxidation Event also underscores a subtle truth: that life's greatest impacts arise from ordinary processes repeated countless times, not from sudden miracles. Each cyanobacterium that split water and exhaled oxygen seemed trivial in isolation. Yet billions acting over hundreds of millions of years changed the trajectory of a planet. This cumulative effect mirrors how carbon emissions, deforestation, and pollution operate today, individually small but globally transformative. As oxygen accumulated, it changed the energy economy of Earth. Fermentation could yield only a couple of ATP molecules per glucose. Aerobic respiration produced more than 10 times that amount. This leap enabled cells to invest in DNA repair, protein synthesis, intracellular transport, and structural reinforcement. Larger genomes and complex developmental programs became feasible. Energy abundance became complexity's engine. This surplus also allowed cells to build defensive systems. Reactive oxygen species can damage proteins, lipids, and DNA. Enzymes like superoxide dismutase and catalase evolved to neutralize these threats. Membranes incorporated sterols for stability. Antioxidant molecules became universal. Even today, our own cells deploy these defenses automatically, a living fossil of ancient stress. On a planetary scale, oxygen established new weathering reactions. Sulfides turned to sulfates, ferrous iron to ferric, methane to CO2. These reactions drew down greenhouse gases and triggered glaciations, but also stabilized climate over the long term. Rocks and life had entered a permanent partnership, each shaping the other's evolution. With oxygen came new ecological roles. Predators emerged, able to chase prey and process energy at high rates. Grazers evolved to exploit microbial mats, burrowing into sediments and oxygenating them. This changed nutrient cycling, benthic chemistry, and the entire character of ocean floors. Reefs grew, filtering water and creating three-dimensional habitats. These structural innovations locked carbon into limestone and stabilized atmospheric composition. Land was still barren rock and microbial crusts, but oxygen and ozone were preparing it invisibly. Clay minerals rich in water, stable under oxidizing conditions, accumulated on continents. Weathering released phosphorus, molybdenum, and other nutrients, setting the stage for future plant colonization. When photosynthetic organisms finally crept onto land, they found a world already partially terraformed by oxygen's long work. In parallel, trace metals catalyzed biochemical innovation. Copper became part of enzymes that transport electrons. Iron built hemoglobin precursors. Zinc stabilized DNA-binding proteins. These cofactors linked evolution to geochemistry so tightly that changes in one reshaped the other. Many of the essential biochemicals of modern life owe their origins to redox conditions established billions of years ago. Meanwhile, mass extinctions punctuated progress. Hydrogen sulfide upwellings, nutrient crises, and glaciations periodically reset ecosystems. But survivors adapted with new metabolic tricks, mirroring the GOE's core dynamic: catastrophe as an incubator for complexity. This pattern has recurred ever since, from the Permian die-off to the rise of mammals after the dinosaurs. Today, the Great Oxidation Event stands as both an origin story and a cautionary tale. It shows that life can alter a planet more profoundly than volcanoes or asteroids, and that such alterations can be devastating before they become beneficial. It reveals a deep link between energy flow and complexity, between planetary chemistry and biological innovation. And it invites us to view our own impact through the same lens. Astrobiologists look to the GOE when designing missions to detect life elsewhere. If we see oxygen, ozone, or other disequilibrium gases, we must ask not only, is there life, but at what stage? Is it on the brink of collapse or the threshold of complexity? The GOE teaches that biosignatures evolve, flicker, and stabilize over eons. Climate scientists likewise draw parallels. The same feedbacks that governed oxygen now govern carbon. Photosynthesis, burial, weathering, and volcanic outgassing still regulate atmospheric composition. Our industrial emissions push this system far faster than natural processes ever did. The GOE warns us that once tipping points are crossed, recovery times dwarf human timescales. Finally, on the personal level, the GOE offers a humbling continuity. Your hemoglobin's iron once rusted in ancient oceans. Your mitochondrial enzymes descend from bacterial ancestors forged under oxygen stress. Every cell in your body carries a molecular diary of that ancient revolution. You are not separate from the GOE. You are its latest chapter, inhaling the same elemental breath, begun 2.5 billion years ago. The Great Oxidation Event also reshaped the deep biosphere, not just the surface. Long before plants rooted continents, microbial communities colonized pores of rock kilometers underground. As oxygen seeped slowly into cracks and aquifers, it changed the chemistry of subterranean life. Iron, sulfur, and manganese cycles shifted, creating new niches for chemolithotrophs. Even today, deep subsurface microbes metabolize ancient redox gradients, living fossils of a world before oxygen reached the sky. This subterranean legacy is crucial to understanding planetary habitability. It means that life can persist even when the surface is frozen, scorched, or oxygenated to toxicity. The GOE may have driven many lineages underground, where they adapted and diversified. Some later resurfaced when conditions stabilized, bringing new metabolisms to the open ocean. This hidden migration shows that the biosphere is not a flat sheet, but a layered system with refugees and reservoirs. In the oceans, the GOE permanently established a two-layer world. Oxygenated surface waters allowed aerobic life. Anoxic depths preserved archaic metabolisms. At their interface, microbial consortia developed metabolic handshakes, passing electrons from iron reducers to sulfate reducers, from methane oxidizers to nitrate users. These redox partnerships mirror the electron transport chains inside our own mitochondria, hinting at a continuity of mechanism from microbe to human cell. Above, ozone formed a true atmospheric shield. With ultraviolet radiation filtered, hereditary material could accumulate complexity. Developmental genes could expand and refine without constant lethal damage. This stability enabled multicellularity to flourish and prepared the planet for colonization of land. Oxygen was not just a resource, but a stabilizer, weaving resilience into the fabric of life. Another dimension of the Great Oxidation Event is its effect on minerals. Before oxygen, Earth hosted fewer than 1,500 known mineral species. Afterward, that number more than doubled. New oxides, hydroxides, and sulfates appeared, painting the crust with unprecedented diversity. This mineral explosion provided substrates for catalysis, nutrient storage, and perhaps even prebiotic chemistry on exposed surfaces. In a sense, oxygen's greatest geological impact was to diversify the chemical toolkit available to life. Many of our most important ore deposits formed in this window. Banded iron formations represent oceans rusting as oxygen rose. Red beds mark continental oxidation. Uranium became mobile, concentrating in sedimentary basins. Copper and zinc accumulated in new deposits. Without this ancient shift, our modern civilization would lack many of the metals on which it depends. Each smartphone, wind turbine, and surgical tool carries an echo of cyanobacteria's breath. This mineral diversification also created new habitats. Porous oxides hosted biofilms, catalyzed reactions, and concentrated nutrients. Clay minerals absorbed organic molecules, perhaps stabilizing fragile compounds and promoting complex chemistry. Over time, these surfaces became cradles for evolution, linking geology and biology ever more tightly. At the planetary scale, this partnership produced a kind of geobiological ratchet. Once oxygen introduced new minerals, those minerals reinforced oxygenation by altering weathering and nutrient cycles. Feedback loops tightened, making Earth more resistant to returning to an anoxic state. The planet had passed a point of no return, locking in a new geochemical regime that persists to this day. For modern science and culture, the Great Oxidation Event is more than an academic subject. It's a metaphor for transformation. It reminds us that systems, biological, social, planetary, can shift from one state to another when small processes accumulate. It also shows that such transformations are double-edged. They can destroy as they create, destabilize as they empower. Astrobiologists use the GOE to build timelines of planetary evolution. They imagine exoplanets where life has just begun to oxygenate the air, worlds poised between microbial simplicity and multicellular complexity. Some may be experiencing their own oxygen catastrophe, wiping out anaerobes even as it sets the stage for future intelligence. Observing such worlds would be like peering back in time at our own. Climate scientists see in the GOE a deep precedent for tipping points. Methane collapse, ice ages, and carbon drawdown echo today's rapid CO2 rise, ocean acidification, and biodiversity loss. Understanding how feedback loops worked then may help us anticipate nonlinear responses now. On a personal scale, the GOE connects every breath you take to the first rays of sunlight filtered through ancient microbial mats. Your body is powered by mitochondria. Your blood carries iron once precipitated in banded iron formations. Your DNA is protected by repair enzymes forged under oxidative stress. You are living evidence that catastrophe can be the mother of possibility. And so, from a world of green oceans and alien skies, through pulses of ice and bursts of fire, the Great Oxidation Event transformed Earth from a planet of microbes into a world capable of forests, animals, and eventually, human minds. A waste product became a power source. A poison became the foundation of breath. Catastrophe became the prelude to complexity. Every mitochondrion in your cells is a living fossil of that ancient revolution. Every lungful of air carries atoms forged in stars, cycled through microbes billions of years ago. Every heartbeat echoes the rhythms of feedback loops that once froze continents and rusted oceans. The lesson of the Great Oxidation Event is not just about deep time, but about now. Small, steady actions can reshape a world. Feedback loops can amplify until a system tips into a new state. Resilience comes from diversity, interdependence, and adaptation. The same principles that carried life through the first planetary transformation and can guide us through our own. As you drift into sleep or contemplation, remember that your breath is older than mountains. Your cells carry ancient defenses, and your consciousness is built on energy pathways forged under an alien sun. The story of oxygen is the story of possibility, of how life endures, adapts, and transforms everything it touches. Thank you for traveling across billions of years with Journey Through Time. Until next time, breathe deeply, look at the stars, and remember the ancient air within you.